Hello, welcome to session 2 of ECE 418 lab course. In this lab, the first part of the lab, we'll be making a MOS capacitor. We'll start off with a silicon wafer, which is 2 inches in size and P-type flow. And we'll go ahead and make a organic metal oxide and semiconductor structure to make a MOS capacitor that we will later on measure to characterize the MOS capacitor characteristics of the MOS device. So let's go on. Start. Alright, the first step is to actually do oxidation on the silicon wafer. So in the first step, we'll be growing something called a dry oxide. A dry oxide is a higher quality oxide used for gate dielectrics and has a better electrical properties compared to the wet oxide. Dry oxide can be grown on silicon by heating up the silicon wafer in a furnace, such as this one over here, and flowing in oxygen while at a certain flow rate. The oxide thickness can be characterized by using a deal groove model to kind of estimate the thickness of the oxide that you grow based on the time and the temperature of the furnace. As you can see, the furnace we are using is a 6-inch wafer furnace that was donated by Intel. It is an old furnace from 1960s that Intel used for growing their wafers, oxide on their wafers. There are 4 different PID controllers on this furnace for each different cube. Cube C is used for doping, Cube C is used for growing red oxide later on in the class, which we will not be using today, but later on we are doing red oxide. Cube B is what we will be using in today's class to grow dry oxide using the flow of oxygen. And as you can see, the PID controllers for Cube B are actually ramping up to the temperature that we need to go to for this process, which is 1100 C. So, and Tube A is the tube we'll be using for doping later on when we are making MOSCAPs. The other component that you need to make sure before you start your oxidation step is oxygen flow. The oxygen comes in from a cylinder that's in the service bay. There are two metrics you need to keep in mind while flowing oxygen. One is the pressure, inlet pressure at which it goes into the furnace, and the other is the flow rate. And based on the amount of flow rate, which is basically a mass flow controller over here, you can change the amount of oxygen that is entering the furnace, and also as a consequence have a certain level of control over the growth rate of the oxide that you grow in your furnace. For this process, we'll be using a flow rate of around 150 here, which correlates to around 1.5 liters per minute. And let's go on and load the wafer into the furnace. Okay, now that the furnace has reached the temperature of around 1100 C, where we want it to be, we can go ahead and start loading our silicon wafer for growing in dry oxide. Now that the oxygen has also been turned on, we need to make sure that we put on personal protective equipment necessary to handle high temperatures of the wafer seams. So the PPE required for this step is a face shield, as you can see over here, and jute gloves, which are the first order of protection from handling the high temperatures. You're actually loading in the quartz wafer board into the... Okay, so we'll be using a quartz board to load in the wafers into the hard tube furnace. For that, we'll be using quartz board for furnace B, so to avoid any cross-contamination. The wafer that is the AID clean 2-inch wafer is kept somewhere in the middle of the board. There's a wafer called dummy wafers that are kept front and back of the actual wafer that we'll be performing oxidation. These wafers are to make sure that the gas flow is kind of streamlined rather than having turbulent flow, so you have an even growth rate of oxide throughout the entire wafer surface. Okay, now that the furnace is open, we go ahead and load a wafer. Now we go ahead and load the quartz wafer color. The wafer surface is going to face into the furnace, so the oxygen actually hits the surface of the wafer that we want to blow outside. Okay, so now the wafer is pushed to the halfway point, where the oxidation is actually supposed to happen. Now that it's 20 minutes, we have switched off the oxygen supply, and we're going to take out our wafers. One important point to keep in mind while taking out the wafers is to make sure that you don't take them out real fast. If you expose them to room temperature immediately once they're coming from 1100 C, a huge temperature gradient can crack the wafers. It's very important to make sure that you pull them out as slow as possible. Okay, now that we have taken the wafer out of the furnace, it's a good thing to do a quick sanity check to see if we have actually grown an oxide. And the way to quickly check this is to see the color of the wafer. As you can see, for different thicknesses of the oxide, you can see different thickness of slightly different color under white light. So for oxide that is around 100 nanometers, you would expect to see a kind of royal bluish to a violet color, which you see for the wafer that is actually put into the furnace. The wafer that is shown at the background is actually a silicon wafer, which is sort of siliconish in color without any specific color as a reference. Cut. Okay, now to actually measure the thickness of the oxide that we have grown, we use a spectroscopic ellipsometer. The ellipsometer we use over here is from Film Sense, which has 6 different wavelengths. There's a laser that is incident onto the wafer surface, and you can also do a quick wafer map to kind of see how the uniformity of the oxide looks like on the wafer. Essentially, how an ellipsometer operates is you have a linearly or circularly polarized light that is incident at a certain angle onto your wafer using the incident polarizer, and the incident laser beam actually undergoes bragg diffraction and comes out as elliptically polarized wavelength light, which is detected by this polarizer, receiving polarizer, and resolved into an amplitude and a phase component from which you can deduce the refractive index and the thickness of your film. Let's go ahead and measure it. As you can see, the oxide is pretty thick. It's thicker than what we expected. We were expecting to grow around 70 nanometers, but it turned out to be around 95 nanometers. This is probably because of a higher flow or maybe a longer time, dwelling time into the furnace. But it is always a good idea to measure the oxide after you grow to compare any experimental effects that might happen. A quick wafer uniformity tells us that it is slightly thicker towards this edge as opposed to the other regions, though there's not a huge difference in thickness. And this could be due to the flow gradients, which is probably the reason why you're seeing a slightly thicker film right at this edge as opposed to. now that we have measured the thickness of the oxide, we can go ahead with the next steps, which involves removing the oxide on the back side of the wafer to make a metal contact. Metal oxide semiconductor contact needs to be on the shiny surface over here, so it is important to protect the oxide on the top side of the wafer or the shiny side of the wafer, whereas remove the oxide on the back side of the wafer, which is grown during the oxidation step. So for this we do it in two parts. The first step is to actually spin coat a photoresist onto the top side of the wafer to protect the actual gate oxide, and then do an etch using hydrofluoric acid or buffered oxide etch to remove oxide on the back side of the wafer, and then deposit aluminum contacts on the back side of the wafer. So to protect the top side of the wafer or the gate oxide on the top side of the wafer, we spin coat using the photoresist. This is a spin coater over here, and there are two crucial components to spin coating. One is to actually spin coat the photoresist on the wafer using a spinner, which is the wafer is held using a vacuum chuck and is spun at around 5000 RPM. Once the wafer is spun, it is transferred onto a hot plate at 115C for 2 minutes to do a quick soft bake. Since hydrofluoric acid etch is not an oxidizing etch, we can get away with doing a soft bake if it is for a relatively small amount of time. An important, crucial point to make sure before spin coating is to make sure that your wafer is absolutely clean, as in the wafer surface doesn't have any particular contaminants. If you have any particular contaminants, you can remove the particular contaminants by blowing the wafer using nitrogen gun prior to spin coating your wafer. Before we actually start spinning the wafer, we need to make sure that the wafer is centered. As you can see, the wafer is kind of wobbling around the center, so it is important to correct for any centering issues. Once it is reasonably centered, we go ahead and dispense our photoresist onto the wafer. It is very important when dispensing the photoresist to avoid any bubbles that might result on the wafer. As you can see, there is one bubble that might have formed on the wafer. Any bubbles that remain during the spin coating process can actually create areas with non-uniformity of the photoresist, so we can make sure that we suck away all the bubbles by using a reverse dispense action. It's also important to not waste too much photoresist, so we can dispense the photoresist on just 2/3 of the area of the wafer. Once it is dispensed, we can go ahead and start spin coating. Alright, once the wafer is spin coated, make sure to not waste too much time and load the wafer onto the hot plate and start the timer. So now that we have spun photoresist on the shiny side of the wafer, which protects the gate oxide, we can proceed to the next step, which is etching the back side of the wafer of the oxide to make sure that we can make a metal contact. Okay. Now that we are going to use buffer oxide etch to etch oxide, there are a couple of things to keep in mind before actually proceeding to the step. Since hydrofluoric acid is very poisonous and dangerous, it is important to use personal protection equipment. And acid protection equipment such as this over here, and nitrile gloves which provide a decent amount of protection to hydrofluoric acid and overcome. It's also important to use a face shield to provide splash protection in case, make sure that it doesn't get into your eyes. Acid etches are done usually using a buddy system where another person, for example, Shirso, who's shooting with me, is going to accompany me while I'm doing this etch. You should make sure that you never do acid etches alone. It's also important to have safety items such as calgonate next to you, so in case there's any skin contact with hydrofluoric acid, you can apply this gel which can leach off any chloride ions that can get into your skin. In case of a spill, make sure to alert your buddy immediately, and depending on the severity of the spill, you can call others, or if the spill is onto the body, make sure to make a 911 call. Okay, now that we have the hydrofluoric acid in this polyethylene container ready for etch, we can go ahead and etch the backside of the wafer. It is important to not use glass utensils for hydrofluoric acid, because hydrofluoric acid etches to SiO2, and glass, if you remember, is made of SiO2. So always make sure to use a polychloroethylene container. Before the etch, make sure to inspect your PPE, especially your gloves, so that there are no wears and tears on the gloves. Any tear can be a potential place where acid can get into your inner glove, which might not give as good protection as it needs, and eventually get onto your skin. So that's not a good thing to want to have. The way about going to do a hydrofluoric acid etch is to make sure everything is ready. Have clear water ready in case of any spill. Let's go on with the etch. We'll take the wafer out. The important thing is to make sure that we etch the backside of the wafer, so we'll keep the backside exposed to the top. And once we drop the wafer inside the HF solution, go ahead and start the timer. Now, the oxide thickness is around 95 nanometers that we measured using oximetry. The etch rate for the hydrofluoric acid is supposed to be around 90 nanometers per minute. So we'll go ahead and etch it for at least 1.5 minutes, so it completely removes any oxide, and we can make a good metal contact immediately using thermal evaporation of that. Okay, now that it has 1 minute 30 seconds, we can go ahead and take the wafer out. Carefully, make sure to not have any splash. It is important to not over etch the wafer as well, so you end up losing a lot of oxide on the front side of the wafer. Once you take the wafer out, immediately clean the wafer with well water, both front and back. It is important to clean any surfaces that might have been exposed to hydrofluoric acid thoroughly with well water. This is to make sure that you don't get any hydrofluoric acid onto your gloves later on once you take the wafer out. The photoresist on the front side of the wafer using acetone. Then make sure that this is thorough, so there is no any residue. Remove any residues from acetone clean using IPA. And this is followed by DA1. The final step is to make sure that you blow the wafer dry using a nitrogen gun. Okay, now that we have finished etching the backside of the wafer, the next class we'll revisit on how to go ahead and deposit a metal contact on the backside of the wafer, and using thermal evaporation, and finally deposit top metal contacts for the MOS capacitor structure using sputtering.